Hello everybody, welcome to this second lecture on cyclohexanes. Before I share the screen, please ensure that you subscribe to the channel if you like the lecture. So let us go to the content. This is cycloalkanes part 2. In cycloalkanes part 1, we had discussed about the stereochemistry of cycloalkanes, mainly cyclopropane and cyclobutane, and some of the stereochemistry of cyclopentane. According to the syllabus, now we will be dealing with methods of preparation and the reactions of cyclopropane and cyclobutane. So, I am Urmila Joshi, and let us start with the cycloalkanes part 2. Given here is my mail ID. In case you have any doubts, you can write to me. Going to the synthesis of cyclopropane. Okay, shown here. The first method for synthesis of cyclopropane is from 1,3-dibromopropane. Look at this. This is 1,3-dibromopropane. There are already three carbon atoms. And what is needed is removal of these two bromines and cyclization. Okay. So that is achieved by sodium. Sodium removes the bromine atoms. The substrate is cyclized and sodium bromide is formed. This reaction is very similar to the Woods coupling reaction, if you recollect Woods coupling. The modified method is using 1,3-dibromopropane but treating it with zinc. What happens when you treat it with zinc? The product is the same. Zinc bromide is formed instead of sodium bromide, but the yield is improved significantly. And therefore, this method is more useful than the first method. This method is called as Freund's method. The second method for synthesis is from 1,2-dibromoethane using malonate ester. Look at this. This is 1,2-dibromoethane. There are two carbons. For formation of cyclopropane, third carbon is required. And this third carbon comes from the malonate ester, diethyl malonate. As you all know, the CH2 of malonate ester can get easily converted to a carbanion. And this carbanion can attack either this CH2 and then this CH2 to form a cyclized structure, as is shown over here. Now, when there are two carboxylates attached to a carbon, when it is heated with water and acid, there hydrolysis of the ester occurs, and this is followed by loss of carbon dioxide. So one group is removed, the other group is hydrolyzed, and so what is formed is cyclopropane 1-carboxylic acid. Okay, why I am calling it as cyclopropane 1-carboxylic acid and not as cyclopropanoic acid is because the carboxylic carbon and these are not numbered in continuation as we discussed in the first part. And so this is not cyclopropanoic acid, this is cyclopropane carboxylic acid. The third method for synthesis, again for cyclopropane carboxylic acid, is from 1-bromo-3-cyanopropane. Forgive me for this mistake. 1-bromo-3-cyanopropane, when it is treated with NaOH, first forms cyanocyclopropane. Okay, this cyanocyclopropane is hydrolyzed very easily in presence of water and dilute HCl to form cyclopropane carboxylic acid. Okay, let us go to the next slide. Fourth one is called as Simon-Smith reaction. Here too, a 2-carbon starting material and another one carbon starting material are fused together to give cyclopropane. Just let us see how. This is methyl diiodide, right? Methyl diiodide is treated with a copper zinc complex in presence of ether. So what is formed is iodomethyl zinc iodide. Okay, this is an easy name to remember because you can derive it, iodomethyl zinc iodide. Now this iodomethyl zinc iodide contains a CH2, and this CH2 is a reactive carbenoid intermediate. Okay, what is a carbene? Anybody remembers? A carbene is a CH2 with 2 electrons. So, a carbene is an electron deficient species. If you realize, there are only 6 electrons in the outermost orbit. So, this is an electron deficient species, and this behaves like a carbene, an electron deficient species. Why behaves like a carbene? This is CH2I, where the electrons are more towards I, and this is CH2Zn, where the electrons are more towards CH2, and so this behaves like a carbene, and therefore called as carbenoid. This accepts electrons from the alkene, and a cyclopropane ring is formed. One thing to remember over here is the stereochemistry of alkene is retained in the reaction. In the sense, if the alkene is a cis alkene, then cyclopropane that is formed is also cis cyclopropane. If the alkene is a trans alkene, then the cyclopropane that is formed is also trans. One example is given over here. This is 2-butene. Okay, when 2-butene is reacted with iodomethyl zinc iodide, CH2 is inserted, but the stereochemistry of the alkene is retained. That is, the resultant product is a cis product. Now coming to the reactions of cyclopropane. As I mentioned earlier, cyclopropane in part 1, cyclopropane is a very strained ring. And because it is a strained ring, this ring opens up very easily. When it is treated with hydrogen in presence of nickel at 80 degrees Celsius, this ring opens up very easily to form propane. Same is the case with halogenation. When you treat cyclopropane with bromine in presence of carbon tetrachloride and in dark. Why in dark is because free radical reaction should not interfere. So in dark. Okay, so when cyclopropane is treated with bromine in dark in presence of carbon tetrachloride as a solvent, what is formed is 1,3-dibromopropane. Okay, again the ring opens very easily because it is a strained ring, and given the first opportunity, it just opens up. Okay, chlorine gives a similar product. So when you treat cyclopropane with chlorine, you get 1,3-dichloropropane. The reaction is different in presence of light. In presence of light, what happens? It is a radical reaction. Okay. So when cyclopropane is treated with chlorine in presence of light, what happens is chlorocyclopropane is formed. Okay. This is chlorocyclopropane. Chlorocyclopropane. Okay. Similar reaction is given by bromine. So when you treat bromine with cyclopropane, bromocyclopropane is formed. This is because this reaction follows a free radical mechanism and gives a substitution product. Coming to halohydrogenation or hydrohalogenation, this reaction, just like bromination or chlorination in dark, also results in ring opening. So when cyclopropane is treated with HBr in dark, it gives 1-bromopropane. Now let us see what happens to the ring. See, this is 1-methyl cyclopropane. 1-methyl cyclopropane, when it is treated with HBr, the Br can go to this carbon or Br can go to this carbon while opening of the ring. The reaction follows Markovnikov pathway, that is Br goes to the more substituted carbon. And therefore, have a look at this. Br goes to the carbon to which already CH3 is attached. And this results in formation of 2-bromobutane. Okay, let us go to the next slide, hydration. When cyclopropane, just a minute. I don't know what is happening. I want a laser pointer, yes. When cyclopropane is treated with water in presence of concentrated H2SO4, trace amounts, of course, giving H plus ions, the ring again opens up very easily, giving 1-propanol. Okay. One thing to be noted is cyclopropane does not react with KMNO4 as well as ozone. Okay. Coming to cyclobutane now. Two important methods for synthesis of cyclobutane. One is from 1,4-dibromobutane, just like cyclopropane. This is 1,4-dibromobutane. If you remove these two, obviously a bond will be formed over here, and this will result in formation of cyclobutane. Another method for synthesis of cyclobutane is cycloaddition reaction. Now, cycloaddition can be 4 plus 2 cycloaddition or 2 plus 2 cycloaddition. 4 plus 2 is a thermal reaction that it occurs in presence of heat, and 2 plus 2 occurs in presence of light. So when there is light, 2 molecules of ethene cyclize to give cyclobutane. Okay. When there is no light and if you provide heat, such reaction will not occur. Okay. Now, coming to reactions of cyclobutane, they are just same as cyclopropane. Just have a look. When cyclobutane is treated with hydrogen in presence of nickel, the ring opens up to give N-butane. The only difference here is the temperature needed is 200 degrees Celsius, whereas in case of cyclopropane, it was 80 degrees. Why so? That is because cyclopropane, as we discussed earlier, is a much more strained ring, and therefore it opens very easily. Now, this is not a strained ring, much less strained than cyclopropane, and therefore opening requires a higher temperature. If you heat it at still higher temperature, it gives you ethene, 2 molecules of ethene. When you treat it with hydrogen halide, again ring opening occurs and you get 1-halobutane. Okay, the hydrogen halide can be HCl or it can be HBr. If you treat it with halogen in presence of light, remember for cyclobutane as well as cyclopropane, when you treat it with halogen in presence of light, the reaction that occurs is a substitution reaction. And so when you treat cyclobutane with chlorine in presence of light, chlorocyclobutane is formed. All the reactions are just same as cyclopropane. The only difference to be noted is cyclopropane opens up much more easily than cyclobutane, again because the strain in cyclopropane is more. Okay. Now here are some questions. The first question is complete the following reactions. I hope you know that this delta means heat. Okay, such type of questions are asked in the exam for 1 mark. You have to write the structure of the product. I have given 4 representative reactions. Then there are some other questions, long questions of 3 to 4 marks. which are mentioned over here. We have discussed everything of this, and if you are able to write a proper answer, that prepares you for the exam. And some more questions on part 1, which were missing in the part 1. Okay, so you can try to write the answers to these. I hope you have liked this lecture. Please subscribe to the channel if you have liked the lecture. Okay. So with this, thank you so much.